There are many sources out there that use the boring, nerdy, nobody likes calculus way of deriving the formula for relativistic additions of velocities. Today, I have decided to share with you the visual, literal method of deriving the formula no other sources have ever mentioned before. We have here a rocket of length L, moving with a velocity of v to the right. In it, a man fires a projectile that moves with the speed of u prime in the direction of the rocket. The reason we cannot simply add v plus u prime to obtain the speed of the projectile in the frame of reference of a stationary observer is because speed u prime is relative to the man in the rocket. To add v and u prime, we'll have to transform u prime to the reference frame of the stationary observer, where u is equals to the transformation of u prime. Just like a passenger in a car, the car moves at the speed of 100 km per hour, but the speed of the passenger relative to the car is 0. The speed u is like the speed of the passenger. Since u is velocity, it can be written as transformed length or transformed time, where time is time taken for the projectile to reach from one end of the rocket to the other, in the reference frame of the observer on the rocket. As a stationary observer, you will notice a few things. The first would be the contraction of the rocket. Looking closely at a clock on board the rocket, you will also notice time ticking slower. Lastly, if each end of the rocket had a clock, you would notice that the clock at the back end is ahead of the clock at the front end. We have the total distance that the projectile travels in the ship, which is length over gamma, and the total time elapsed due to time dilation only is length over u prime times gamma. Formula for the difference in time between 2 points is length times velocity of the rocket over c squared minus v squared, and the total time elapsed is this. If you were quick enough, you would notice that speed u is not dependent on L, which makes sense since the length of the rocket doesn't affect the motion of the projectile. We can simplify the equation to this, and so on, until we reach this. Now, we know that gamma equals this, and substituting it into the equation would give this would be the speed of the projectile u. Going back to the analogy of the car, even though the passenger has a speed of u equals 0, he is still moving with a speed of 100 km per hour. The absolute speed of the projectile would be v plus u, which would simplify into, and further simplification would result in the formula. Let the length of the rocket be 0.866 light years long, moving with a velocity of 0.866 the speed of light, with a projectile moving with speed u prime of 0.866 c. This specific speed will give you a gamma factor of 2, which makes things much easier to understand. The time it takes for the projectile to reach the end of the ship is 1 year. To someone stationary, it would seem to take 2 years to cross 0.866 light years over 2, which is 0.433 light years. Then there's also simultaneity, where the time difference between both ends of the ship is 1.5 years. So the speed of u would equal to 0.1237 c, and the final speed of the projectile would be 0.9897 the speed of light. All added velocities have to be adjusted into the stationary observer's frame of reference. When the stationary observer gazes at the rocket, they would notice the projectile in the rocket traveling a distance of L over gamma, and the time taken to travel that distance by the projectile would be L over u prime times gamma plus length of rocket times speed of rocket over c squared minus speed of rocket squared. The calculus method of derivation would only give you the formula for relativistic additions of velocities. However, this method of derivation tells you exactly what actually happens.